in groups or in every kind of mathematical structure. And the most important types of morphisms are those which are invertible, and that these are called isomorphisms. So sense. Now let's commutative ring with unity. And V and W are modules. And F is a linear map. Okay. And we say that F is an isomorphism between V and W, of course, and that V and W are isomorphic. Okay, and no. If there exists homomorphism in F is bijective. So if it's bijective, its inverse is automatically linear. F is bijective. Okay. And V and W are called to be isomorphic. They are isomorphic as R modules. They might not be isomorphic as other structure. This is the common theme in mathematics. Two things can be isomorphic or not depending on the structure. And we write this, right? Denoted by V is isomorphic to W. So we have two like equal sign and tilde to the top of it. Okay. Oh, before giving examples, okay, let's now give one example, then I'll give more. But so start with our module. Commutative ring with unity. And take integers, and V is the space of matrices, and W is the, to what degree I should, how many the dimensions my space of tuples should have to be isomorphic to the space of matrices. I have to put m times n. So then the map, the following map, V to W given by, so we start with a matrix, A11, A1n, AM1, AMN. So with just let's and so on to AM1, AMN. So we take all the elements of the matrix and flatten them. Is an isomorphism. Okay, so this is simple example. So matrices can be taught as vectors sometimes, and it's useful, but sometimes it's useful to look at them as linear operators. Okay. Now let's give some proposition, which I should have given before, but I forgot. So so the idea of this needs to know on a basis to be able to restore the real matrix. Let R be an commutative link with unity. V and W be R modules. And V has a basis. V is free with a basis as it can be infinite, but let's fix with finite. I just put in brackets that it can be infinite as well, as can be infinite as well. Then let's take some values in W. So let W1, Wn are in W. Then so take let V be in V. Then there exists, so since E1 to En the basis of V, V has unique representation, has a unique V is lambda 1 E1 plus lambda n En, where these are scalars. Lambda 1. And so we define how to define f of V. Lambda n Wn. And the details now, for it can be seen that this is uniquely, it can be seen. I will not go to in the details, be seen that if you want, you can try it. Finish the proof. Usually it's much easier to define some operators on basis when we have one. For example, let's consider some commutative ring with unity. Some integer and some finite space. Integer and some finite space. S is E1. It's a finite set. It's a finite set. Then the point map. Then F from Rn to the free vector space, the free module, sorry. So remember, the free module is the set of all formal linear combinations. So we define this in that way. So F defined by F of 1, 0, 0, 1, 0, and so on equals E1, and F of 0 to 1 equals En. F of 0 to 1 equals En. So we define it for basis elements and extended by linearity. This is the terminology. And extended by linearity is isomorphism. Now, in this particular case, it may be easier to define it directly. Direct definition. Well, any vector is a combination of these things here. So f of, let's say, lambda 1, lambda n. This would be the lambda 1 of this thing plus dots to lambda n this thing here. And we'll map this to lambda 1 E1 plus dots to lambda n En. Lambda n En. Lambda 1 E1 plus lambda n En. So this is the direct definition of F. Okay. Okay. Another example, very important. So consider some vector. Fine. It's like in the other direction. So So consider some vector. Fine. It's like in the other direction. So consider R module. And V be a finite dimensional an R module of dimension n. For any basis E, which is E1 to E, an ordered basis. So let's say it's ordered. Any ordered basis E1 basis E1 E1 to En. So we take some basis and ordered elements. Now we define the coordinate map, maybe. I've seen it with square brackets, maybe with I will use circle brackets. So it's like that. This dot here means that the argument will be put here. So it's from V to Rn. So we define by this way. V if as follows. So we take a vector and V equals to lambda 1 U1 plus lambda n En. Then the coordinates of V in the basis E are lambda 1 to lambda n. May be written as a column vector. Okay. And this is a linear map. And it is a linear map. And also linear, it's in isomorphism. In fact, isomorphism between V and Rn. And this isomorphism is different for any basis. So for any choice of a basis E, we get a different isomorphism. If we change coordinates, it will be different, but to change coordinates, we need to talk about how coordinates are changed. Let me give some example here for this thing here. Maybe this was not example, this was definition. Let's rewrite the definition. and give some example here. For instance, polynomials. So V is a set of, again, squared polynomials. A0 plus A1 x plus A2 square x squared. With basis, here there are real numbers. It can be any ring, but let's pick real numbers. And we define F from V, no, sorry. E is the basis 1, x squared is the basis of V, the standard basis. And we can map a polynomial to triple. So a square polynomial is in some sense equivalent to a triple of numbers. So it's f of a0 plus a1 x plus a2 x squared is this. A0, A1, A2. So sorry, this was the map, this map here. So maybe this in this basis, yes. So we can, for any vector space, we can represent its elements by vectors. For linear operators, we can also do that, but it's better to represent them as matrices. So first, let's give some kind of, it's mixture between definition and proposition. Okay, proposition. Let I always forget to say it's continuity. V and W are R modules. R modules. Then this thing here. This is a sub. So the space of linear maps is also R module. It's also linear space if it was a field. So is a submodule of the space of all maps of the space of the module space. Last time I defined the space of, or maybe a few times, a few lectures ago, V to the power of V. So this is the space of all maps F, where F is from V to W. All functions. Not only linear, but all functions. And I say that it was a module over a ring, and here I say that it was a module over a ring, and here we take a submodule. So we can add and subtract and multiply by number linear maps. So let me just remind. So if F and G are linear maps, then F plus G is a linear map. F plus minus G doesn't matter. And if lambda is a scalar and f is a linear map, then we can multiply the map by a scalar. It's also a linear map. So it might be sound strange for the first time that you can add subtract vectors, but then also the maps itself, and you can you can form a more complex spaces like the space of all linear maps from this thing to other thing and so on. Okay. Now I will show that this space corresponds to the space of matrices. Oh, sorry, proposition. Or maybe definition. Let's see. Yeah, maybe definition. It's a mixture of definition and facts. Or maybe some example. Let me give some example. My favorite space polynomials of degree 2. My favorite space of today. And let's say f is the derivative operator. G is the identity map. And let's consider, for instance, the linear combination H equals, I don't know, 2f minus 3j. Then H of something here. So this would be 2 times this thing prime minus 3 times itself, because G is the identity. Minus 3 times itself. Minus 3 times. And so this linear map will be 2 times a1 plus 2 times a2x minus this thing here. And we collect the coefficients. So this will be minus 3 times a0 plus, so 2 times a1 minus 3 times a0 plus 2 times 4 times a2 minus 3 times a1x minus 3 times a2x squared. So we got something like from A0, A1, A2, we got to by H in some basis. It's not, this is not exactly rigorous. I will need the next thing, the next definition to become rigorous, but from this thing via H, we got these coefficients. We got 2A1 minus 3A0, 4A2 minus 3A1, and minus 3A2. We got things like that. Okay, now let me give the definition I wanted to give. As usual, as always, start with commutative link with unity. V and W, they are finite dimensional. Are finite dimensional. Choose, and for any basis E n of V and V F of W, define the following the isomorphism phi from the space of linear maps to the space of matrices from of dimension n times n by as follows. So if for E in, or sorry, for I from 1 to M, no, from 1 to, for G, from 1 to N. So we take and take some isomorphism. So take an isomorphism for N, and let's mind it curly A in if A of EI. So A is a linear map from V to W, and it's defined, it's can be reconstructed by its values on a basis. The basis is E1 to En. And we apply A to EI and get element of W. But this is a linear combination of these bases. So this is A. So this is G. A I J E F1 F A A1 J F1 plus A1 A M J F M. Then define the following. F is, so this should be M times, so this should be M times N matrix. A11, AM1, A N N. Let me see if everything is fine. Sorry, this isomorphism should be like not phi but EF. One. Yeah, that's fine, I think. Now let's give example. So this is how you do any linear isomorphism, any linear map between finite dimensional spaces. For example, I use this thing here. So I will just continue this thing here. From above, we have that this thing here, H of A0 is minus 3A0 plus 2A1 plus 0A2. H of A1X. So H of sorry. The basis element is 1. No, this thing. So my basis E equals F is the following basis, AX x squared. And I see where anything goes. So H of 1 is, so this is my result. This means that A1 and A2 are 0 and A0 is 1. So we get minus 3 and that is H of X means that A1 equals 1 and other two are 0. So we have 2 times A1, sorry, 2, and then minus 3 times X. and h of x squared, what is this? We have here, that means that a2 is 1. So we have 4x minus 3x squared. And the matrix of H in this basis is, so we take minus 3, 0, 0. So we take this thing here and put it on a column. So you see this thing here is like this, and this goes the jth column. Then we have, this is 2 minus 3, 0, and this is 0, 4 minus 3. Andre, can you see? I see in your head. So now, why is this definition made that way? We have very interesting proposition. So that's why in more elementary courses of linear algebra, everything is done with matrices. Because for finite dimensional spaces, all vectors can be represented as tuples, and all operators can be represented as matrices. But the thing is, operators are much more general, and when you don't choose a basis when you work with them, so they represent the internal structure of the things you work with better. So for instance, I have some operator here like derivative. I can choose another basis. If you've heard about, there are some polynomials used in numerical linear algebra, numerical methods. For instance, Legendre polynomials and things like that. And there the basis is not this one. And the matrix of the operator will be different. Here I have the basis, the two bases being the same, but in general they can be different, but I'm not giving example. I just want to to give a, to show why is this done that way. So and we'll finish with that. So let R be on a CR commutative link with unity, and I'll take three finite dimensional modules. So U, V, W are finite dimensional R modules. And take two linear maps. So, okay, let's give them some basis. No, first define the operators. So, P is, let's go with A and B maybe, I don't know. A is a linear map from V to W, from E to V, and B is a linear map from R from V to W. So we have just U, V, and This is what we have. I forgot to say, but the composition of linear maps is linear, I will say now. So then B, and it doesn't need to be, it can be any modules. They don't need to be finite dimensional. But the composition is, oh, this here, is a linear map from U to W, and if E is a basis, okay, it's a basis of U, F, and P. Doesn't matter. Let's call this P, F, F1 to Fm is a basis of V, and G, well, is a basis of W. So if we have this basis, then we have the following. So we have the matrix of A in the basis. So the matrix of A in the basis EF is M times P. The matrix of B in basis FG is M n times P. And the matrix of B composed with A from E to J is so we go from it's not NP. So I made a mistake. So sorry. It's n times m, I think. Yeah. And the matrix of this here is n times p. So we have these things here, but the most important thing is the following equation. The composition is B E F I made some mistake. Maybe. Some mistake. Maybe. Sorry, I think this looks fine, but I think it should be the previous definition. It should be the other. It should be like that. Maybe. I'm not sure. I just
In the previous definition, we had E on the top. Like that way.
Yeah.
Because of the shit you had that way.
Yeah, but I think it should be other way. It doesn't matter. It works fine, but because the indices of E they're going to the top, does it looks fine? Because they should cancel out from that diagonal, not from that diagonal. You see, like this F cancel out, but they should cancel out in the other diagonal. Let me think. But if the definition is like that, it looks fine, isn't it? G to E. So yeah, maybe in the previous definition, I want to be that way. So I want to be GF and here FE. EG. So maybe in the previous definition, just swap the. So what does this tell us? That if you have chosen basis, an composition of operators corresponds to multiplication of matrices. So composition of operators of linear maps is like matrix multiplication, but only in the finite dimensional case, matrix multiplication. Okay. Yeah, okay. And last thing before, I think we're over time, but I just want to stress the vector space V and VE, then A in A. So this is in V is in W. So this should be B here. And B V in the basis J is like V in the basis G F times V in the basis F. Yeah, so again we have canceling on this diagonal. So yeah, so again we have canceling on this diagonal. So operator times vector is like matrix times vector column vector. Okay. Because it should be B. Because this should be a separate definition, but because I don't want to copy everything, in this definition, B is from V to W. So yeah. So operator times vector is like matrix times common vector, and composition of operators is like multiplication of matrices. Okay, and I'll finish here.